Hello everyone, welcome to the third lab, which is on simulation of dynamic systems. I think this will be a lengthy video, but bear with me. Okay, so here are some learning objectives. You should read those. And the first thing we're going to do is learn how to get information about a Simulink model that we have. So to do this, we're going to provide the syntax here. We're going to find the sizes, the initial conditions, and the states for a given model. So what are sizes? Sizes is an array of integers that tells you information about the model. Each index of the array is dedicated to some aspect of the model. For example, the first index tells you how many states there are in the model. If you remember from my last office hours, we did a simple spring mass system which had two states, and our states array therefore had two entries, x and x dot. Our first example is simple. We will run this line here to provide us with the sizes, initial conditions, and states for the forced simple pendulum model. You should open up this model before you run and make sure that it is in your directory, so that way MATLAB can access it when you want to run this line. And you can do that on the top of MATLAB. You should have some file path, and you can select which file path you want to do. Make sure that you see this file here. Okay, so if you run this, here's our sizes array. So we have 2, 0, 0, 0, 0, and then a 1. So as we said, the first index is the amount of states, and as we know, there's two states in a pendulum, right? It's just 1 degree of freedom, and the equation of motion highest order derivative is 2, so we're going to have x and x dot as our states. And then 1 down here tells us if the Simulink model is continuous or discrete, and 1 means it is continuous. Here's the initial conditions that are entered into those integrator blocks. And the states are our position and velocity, just as we expect. Moving on to slide 7. Now we know how to get information about a Simulink model, but we can also run Simulink files from a MATLAB script or from a command window. To do this, we use the sim function. All we need to do is input the model name, the simulation time, and any options we want to run with. Here, if we put look at this table here. If we put the number 1 into the time span input, or sorry, if we put one input, one integer into the time span, so just like some number here, then the MATLAB tells Simulink to run it for that amount of time. So 4 seconds, it'll run from 0 to 4 seconds. If we put two numbers, then the simulation will run from the first number to the next number, and our output times, if we have, say, an array of times, then it will simulate at each of these times. For example, 0 to 4 in increments of 1 millisecond. If you input that array there, it'll run at those times. For the options, here is a bunch of options you can pick from. Here we're going to use relative tolerance with a value of 1 times 10 to the minus 4. And we're going to use the ODE for solver. So this is our options that we can get. Notice we're using SimSet to pick our options. SimSet, the option, and the selection within the option. Here's another option, the solver type, and our selection within the option ODE for. Okay, slide 9. Here's some more options. And slide 10. So our second example will have us run the forced simple pendulum, and we want to find position and velocity. So here's the code that will provide position and velocity. Note that if you're copying and pasting the code, which you should all be doing, run the code, make sure you understand it. You might need to redo all of the apostrophes. MATLAB might give you error, doesn't recognize it when you copy and paste it over. Just redo them. I had to do that. You might also need to add underscores, so Here you see force simple pendulum. It might copy and paste without these, right? These guys in between force and simple, right? You need to make sure those are in there. Okay. Your states are going to be stored into X here. So just like they were last week, you're going to need to print the right column like you do here. Remember from last week, you had to do that. Okay, and here's the outputs. You should give it a try. So now we can find model properties and run models from MATLAB. The next thing we will learn is how to find equilibrium points in a system. Here we see a system in the form where the derivative of the state is a function of the state and some input forcing. For a state space, we note that it is linear. It is linear there's a linear relationship between the derivative of the state and x, right? They're just related by some A matrix. Here we're just generalizing it. We're saying, okay, the derivative of the state is equal to some function of the state itself times some forcing. And we know that the equilibrium occurs when the derivative of the state is equal to 0. So if the state variables are x and x dot, then the derivative of the state will be x dot and x double dot. So this is what the trim command does. It uses that to find equilibrium and partial equilibrium. What is partial equilibrium? So when all of the derivatives of the states are equal to 0, you have equilibrium. That means that both the velocity and acceleration, say, are equal to 0. But a partial equilibrium is when, say, only the velocity is equal to 0 and the acceleration is non-zero. Okay, moving on. Here are the inputs and outputs for the trim function. The important ones are x and x naught. So x is your states that that's going to be the equilibrium states, and the x naught is your guess. So it's going to find the equilibrium closest to your guess. So please read all of these and understand them. So here's an example of the simple pendulum. The states here will be theta and theta dot, right? Because our highest derivative here is 2, so is theta double dot, so our states will be theta dot and theta, which means the derivatives of the states will be theta dot and theta double dot. So we'll set those equal to 0 here, and we're left with this equation. And if we go further to say that our input torsion is equal to 0, then we can say our equilibrium points are 0, plus or minus pi, plus or minus 2 pi, and so on. What does this mean? It means that if you place the pendulum at the bottom here, with no initial velocity, theta equals 0, theta dot equals 0, it's just going to stay there. The same can be said for theta equals pi. If you put it here, theta equals pi, theta dot equals 0, it's just going to stay there forever. Of course, this is unstable because just some slight disturbance will send it swinging around, whereas here, when it's more stable, some slight disturbance isn't going to change the system that drastically. In an unstable equilibrium, it can completely change the system and set things moving. So to do this in MATLAB, we will input the model name into the trim. We'll also put our initial guess for where the equilibrium is, some initial forcing, and the initial output guess into the trim function. And as we expect, our equilibrium is at 0, 0, right? So we're going to guess that an equilibrium is at theta equals 0, theta dot equals 0, and that's exactly what we get here. Here we're doing the same thing, except for we're going to find the equilibrium point around theta equals pi and theta dot equals 0. We know that there's an equilibrium point here, right, because we solved it here. So we're going to guess around this point. We're going to say theta equals 9/10 pi, which is about, 2.8 something. And theta dot equals 0. And we come back with about pi. So we're off by, I don't know, 0.06. So pretty dang close. even though we started a little bit below, it was able to find that closest equilibrium point. Let's move on to linearization. We know that the derivative of the state is a function of the state itself and some input forcing u. We can use equation 4 to linearize the system around an equilibrium point. Note that equation 4 is an approximation. To do this in MATLAB, we use linmod and linmod2, which are for continuous systems. We can use dlinmod for discrete systems. So simply input the model name, the state to linearize about, forcing to linearize about, and perturbation information. Please read and be familiar with all of these variable names. So let's use a simple pendulum example. This system is not linear because there's a sine theta term in the equation of motion. So let's linearize about 0, 0 and pi 0. So those are the two equilibrium points that we found previously. So this slide shows how to do calculations. This is what MATLAB's doing, behind the scenes. Okay, in MATLAB we use the while it's doing, this, what we see is, just this code here. So I'll use the linmod function. We'll input the model name and the point we want to linearize about, 0, 0. And the A, B, C, and D matrices that it spits out are the state space matrices. So state space, as we know, is linear. So if you input a nonlinear system, linearize it about an equilibrium point, it'll give you the linear matrices, or the matrices in order to construct a linear model.